Hi everyone, it's time to do section 6.6, which is our switch over to rational functions. Let's jump right in. What is a rational function? A rational function is a function of the type, someday I'll learn that, y equals. So it's really like f over g. It's like a quotient of two functions where both f and g are polynomials. So it's a quotient of two functions that both are polynomials. Now, the parent rational function is y equals 1 over x. So 1, believe it or not, it is a polynomial. Remember, it's just a constant function, but that's okay. Still considered a polynomial. X is that first degree polynomial. So 1 over x is the parent function for all rational functions. All rational functions have asymptotes. And this parent function, well, not all, I shouldn't say that, most rational functions. But the parent graph, y equals 1 over x, has what's called a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And if we sketch the graph, what ends up happening is our graph kind of gets really close to these asymptotes and curves along like this. And then in this direction, curves like this. And the name of this shape is called a hyperbola. These two opposite facing curves end up generating a shape called a hyperbola. All right, so we're going to move into some translations. So for our first translation we've got, or transformation, we have y equals 1 over x plus 1 minus 2. Remember, if we add to the input, this shifts the whole graph left by one place. We subtract from the output, this shifts the whole graph down 2 places. So if we sketch our graph, always start with the asymptotes. Typically, the vertical asymptote is at x equals 0, but it's been shifted left 1. So now our asymptote is over here at x equals negative 1. Our horizontal asymptote is normally at y equals 0, but it's been shifted down 2. So now we have a horizontal asymptote down there. Your graph has the exact same shape, just new location. So you end up with something like that. This guy has not been translated. It's just been dilated by a factor of 3. All that does, asymptotes stay in the same place. Everything stays in the same place. So vertical at 0, horizontal at 0. However, instead of starting at the point 1, 1, which is where we kept starting for all of our graphs, we multiply our y values, everything by 3. So now it's going to kind of stretch it up here at 3. And then at 2, just plug in a 2, you get 1.5, and then so forth. So it's still going to look pretty much the same, just a little bit stretched out. And then same thing down here. Pretty much the same as the original parent function, just a little bit stretched out. To be honest, I am not that concerned with your individual points being perfect. I'm much more concerned with your asymptotes and the shape of your graph. All right, let's learn how to find those asymptotes. So vertical asymptote, in order to find the vertical asymptote, you're going to set the denominator equal to 0. Because a vertical asymptote is a place remember when you divide by 0, it's bad, right? So if any x value that causes us to divide by 0 is going to cause a problem on our graph, and that's what generates that vertical asymptote. So our vertical asymptote for this graph is the line x equals 3, and it's important that you have the x equals and the number for the vertical asymptote because it's an equation of a line. So it's the vertical line x equals 3. To find x-intercepts, you set the numerator equal to 0 and solve, because x-intercepts are where y equals 0, right? So you're really setting y equal to 0, but y is 0 only where the top is 0, not the bottom. If the bottom is 0, we have a vertical asymptote. If the top is 0, we have a true 0. So we end up with an x-intercept of negative 1, 0, because our x is negative 1 when our y is 0. To find the y-intercepts, you do the opposite. You set all your x's equal to 0, so you get 0 plus 1 over 0 minus 6, and our y-intercept the y value is negative 1/6, and of course the x value is 0. All right, so for this one, for our vertical asymptotes, set the denominator equal to 0, x squared equals 4. If we square root both sides, we get x equals plus or minus root 4, which is 2. So you have a vertical asymptote at negative 2 and a vertical asymptote at 2. X-intercepts, set the top equal to 0. So you get x squared equals 9 when you add 18 and divide by 2. So x would be plus or minus the square root of 9, which is 3. So we actually have two x-intercepts. We have one at 3, 0, and we have a second one at negative 3, 0. Y-intercepts, remember, set all your x's equal to 0, negative 18 over negative 4. So, and that reduces to 9 halves. So we have a y-intercept at 0, 9 halves. All right, let's do practice with graphing. So for this first one, for our vertical asymptote, set the denominator equal to 0, solve, and you get x equals a half. So our vertical asymptote would be x equals 1/2. Your domain is all reals except your vertical asymptote. So it's all reals where x does not equal 1/2, which you can write in interval notation if you wish. The end behavior asymptote we have not learned how to do yet. For now, I'm just going to tell you that it's at y equals 5, and that's all I'm going to do. X-intercept, for our x-intercept, this was our vertical asymptote. For our x-intercept, we set the top equal to 0, and we get x equals 4/10 or 2/5. So we have 2/5, 0. For our y-intercept, you set all your x values equal to 0, and you get negative 4 over negative 1, or 4. So we have 0, 4. When we sketch the graph, start with your asymptotes. So we have a vertical at a half. We have a horizontal at 5. And then plot your intercepts. 2/5 is like right in here. It's just to the left of a half, so it's kind of squished in there. And then our y-intercept 0, 4, so that's up here, which means our graph, I'm going to switch colors here. Our graph is going to kind of squish in here. It's really squished. It's kind of butted right up against those asymptotes. If you want some points, I can tell you that this is going to be on the opposite side, but if you're not sure, just plug in a number, like plug in a 1 into your function, and you get 10 minus 4, which is 6 over 1. So we have the point 1, 6, which is here, and then we're going to kind of squish and squish along our asymptotes. And there we have our graph. All right, one more example and then we're done. So for our vertical asymptotes, we set our denominator equal to 0. We get x equals plus or minus 2, plus or minus the square root of 4, which is 2. So we have x equals 2, x equals negative 2. Our domain would be all reals except 2 or negative 2. End behavior asymptote, all I'm going to tell you is that it's y equals 2. We'll learn why in a later lesson. All right, so for our x-intercepts, set the top equal to 0. All right, so when we factor this, 2x and 3 and 7, we want a positive 7 and a negative 6. It's hard to see from the equation, but because we have 2x squared plus x, we want a positive 1 for our inner and outer. So we end up with x equals negative 7 halves, or x equals 3. So we have 3, 0, and negative 7 halves, 0. Last thing we have to find is our y-intercept. Just set all the x's equal to 0. You get negative 21 over negative 4. So our y-intercept is positive 21/4. All right, let's sketch it. So we have a vertical asymptote at negative 2, a vertical asymptote at 2, a horizontal asymptote at 2. All right, let's plot some points. So we have a point at 3, 0. You know what, I'm going to switch colors here. So 3, 0, negative 7 and 7 halves is just negative 3.5, 0 right here. And then 0, 21 fourths, which is 5 1/4. 1, 2, 3, 4, 5, like right around here. All right. You do not have to plot points. Your far left side and far right side will always follow the asymptotes. So as long as you know one point in there, that's all you need. And then you follow the asymptotes from there and your graph will be fine. For this guy right here, this middle section, there's several ways the middle section can work, but I'm going to tell you it's not going to go cut through the horizontal asymptote for this graph. It can in other graphs, but it's not for this. And how do I know? Because there's no other x-intercepts, and therefore it cannot cross the x-axis, which means it's going to have to go kind of more like a parabola. It's going to go up on both sides. So if you want to plot a point or two, like if we plug in a 1, then we get 2 plus 1 is 3 minus 21, negative 18 over what, negative 3. So we get the point 1, 6, 1, 1, 2, 3, 4, 5, 6, right? If you plug in a negative 1, we get 2 minus 22, so we get negative 20 over negative 3, which is, 6 2/3. So it's not perfectly symmetric, but it is going to go something like that. And there's your graph. Have a great